Assalamu alaikum, guys. Welcome to our new lecture. This is our lecture 4. The last lecture we have in lecture 3, we have discussed about noise, the characterization of noise, various properties, especially the AWGN, additive white Gaussian noise. And because that's the noise adds on the channel, so we term that channel additive white Gaussian noise channel. Today we will discuss on communication receiver. So digital communication receiver. So we have already seen that if we transmit a signal xt which goes through a channel where the signal is mixed up with noise in t, we already have seen this yt, right? The output signal yt. Now this yt signal, the signal we receive needs to go through some operations, means actually in the detection stage. So the received signal yt in this stage would go through a filter having a function ht. So this is a filter. So this is a filter where the impulse response of the filter is ht. This filter actually for a specific system, LTI system, right? So linear time invariant system. From the filter, the signal goes, the output of this filter is RT. Then it goes through some sampling process. So this is a sampling happen here, sampling. And then all the other detection process. So detection, other detection process. Now in this sampling, the signal is sampled at t. Remember our signal what we transmitted here was a pulse signal, right? Having a pulse duration or symbol duration t. So sample at t means here t is the symbol duration. Symbol duration. Now what is the here up to this we have derived the signal yt. Up to this we know, right? Now what happens at rt? What happens at rt? So the signal rt after the filter, the signal will be input is yt, and this is a filter having an impulse response ht. So this signal will be convoluted. So what is this ht? For ht is the impulse response. Impulse response of linear time invariant system. So HT is the impulse response of the LTI system, or it's actually the response of the filter. Now the received signal RT output of this section. So output of this section, the input is YT. It goes to a impulse response HT. The output is RT. So the RT will be the YT, the input, and the impulse response convoluted. Right? Now, what is this convolution? You know what is this convolution? So convolution is a mathematical operation, right? Of two function. Convolution is a mathematical operation of two function. Here, this two function is YT and HT, which produces a third uh, function. Here, in our case, third function is RT. So convolution is a mathematical operation between two function, which produce a third function, and this convolution express how the shape of one is modified by other. This convolution gives what? Shape of one modified by other. For example, shape of YT, which is actually input here, will be modified by HT, modified by the other on HT. The output is a convolution. So how the convolution operation actually done? How the convolution operation is actually done? The convolution is nothing but the product of two functions. Convolution is nothing but the product of two functions. So we definition. Definition. So convolution is nothing but the product of two functions. So product of two function. After one is reversed and shifted. Product of two function and one is reversed and shifted. And shifted. That's the definition. That what we do actually, we do the integral of all. Then integral all. Now, if I make it as a general definition, that convolution is an integral of product of two function where one is reversed and shifted, where one function is reversed and shifted. Right? Okay. So how can I write this equation, write this function RT? So we can write this function according to this definition. So integral of all. So we will integral minus infinity to plus infinity of two product, right? Product of two function, of two product function. One product function is Y, another product function is H. Okay. One is reversed and shifted. Okay, one, another will not. So let's keep H as H. So tau, d tau, because it will be integrated. So one is reversed. Y will be reversed. Y will be reversed. So typically we should I should write Y tau, but because this will be reversed, so it's minus tau. And shifted. So t. So we add both, right? By tau, introducing tau, minus tau, I have reversed it by introducing This t I have shifted it. Okay. Okay. This is the equation for convolution. So this is the total convolution. Convolution. Now, I like to give you some insight of this equation. Okay. For example, I do not know how the signal y looks like. How the signal y look like, I do not know. How the h looks like, I do not know. I am just assuming. Okay, just arbitrary. Huh? So for an arbitrary operation, okay, let's see how they will convolute it. What does it mean actually? So there is an ht, which is the response of the filter, and y t actually, yt signal. So let's draw them. So how should we can just, I'm assuming shape of two signal. Square will be, we cannot see change in the square, so triangle will be better. So let's draw a triangle signal. So this is a triangle signal. So in this axis, this is a triangle signal. Another, let's say both are triangle. So in this axis, both are triangle signal. Okay. Now, this one, let's say this is h tau. This is h tau signal. This is y tau signal. Okay. So this is tau. This is tau. Okay. So this will be like 0, 1, 2. I'm just scaling it. Okay. There is no relation with this practically. I'm just assuming it's a shape. So 0, 1, 2, 3, this way up to tau. Age goes. Y also do the same. So imagine we starting from here. Okay, let's, for a better understanding, let's modify it little bit so that we understand the reference. So imagine this is 0, this is 1, this is 2, this is 3, this is 4. Same thing here, just for better understanding. Sorry. Okay. So this is the signal, and this is our shape. This is the shape of the yt. Okay, a triangular. So this is 0. This is just 1, 2, 3. Okay. So this is the shape of these two signal. Okay. Here you see h tau is not changing. We are only changing y and this one, right? So y, if this is the y tau, how should the y's minus tau looks like? If y is a function of 1, 2, 3, if y minus tau will be function of what? So this is the same axis here. Okay, this is the same axis here. I'm writing. So if it's minus tau, if I want to write y minus tau, what will happen? 1, 2, 3 will be minus 1, 2, 3. Okay, so minus 1, minus 2, minus 3. So 1, minus 1, minus 2, minus 3. So this will be the signal now. This one. So this is now y minus tau, the signal. You see, we just did what? We reversed it. In our definition, we have to reverse it. So this is just reversed. This one just got reversed. Now we have to add t minus tau, right? Okay, same signal, t minus tau. So in the same scale, if I put it in the same scale, if I put it in the same scale, you see in this scale our ht was here, 1 2 3. Our ht was here, 1 2 3, this, right? And our y, now I have to draw y minus tau is already there, so t minus, so you see t minus tau, this is t minus 1, this is okay, this is t minus 1, t minus 1, this is t minus 2, this is t minus 3. It's actually is big, this signal is little bit bigger, sorry, it should be here, so t minus 1 here, t minus 2 here, t minus 3 here. Okay, okay, now this is the signal. Okay, let's say this is 3, so this is y t minus 3. We have shifted the signal, reverse and shifted by adding this t. So I'm satisfying this one, shifted. Before it was reversed, now it's shifted. And integrate all. Integrate all. How we integrate these two signal? Actually, they are product, product of two. So they are have to product of two. How you product of these two signal? You have to make them close, right? So this whole part of this signal, which is actually here, 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 we say this part is t minus 1, t minus 2, t minus 3. This signal and this signal, they has to be product. This signal, h, this is our h tau. This is our y tau. So h tau, how you product this two signal? You have to bring this signal close to him. Like you will be shifted. The whole signal will be shifted there, like little bit, and integrate little bit, integrate little bit, integrate. So if I just, for example, this signal just touch this signal, what will happen? This signal is here, so let h tau will not move. H tau will not move. Only t minus tau, it will move because tau is changing. From, if you change the tau, then signal will be moving. So signal will be moving. So let's touch them. Let's bring it here, close to here, this point. What will happen? So this signal, it will remain here. You see, this guy, he will remain here. This guy, he will be moving. So we will be moving him close to this way. This is the signal. The first instant. Whatever the overlapping, integrate. For example, this is the small area, so integrate this area. In the next stage, this guy remains here, same, but this guy, he actually moves in. So see, moves in, he moves in. So this is the overlapping point. Integrate this point. Okay, it will keep continuing. For example, right? So in the next time, it will be here, and the y, they are all y. Y t minus tau is moving, so it will be moving more probably. So now this part is the integration. So actually, this is actually happening here. This is actually happening here. Here. H tau remains same. Why? By changing the tau is getting and having product and overlapping, and that overlap is integrated. That area is integrated. That's actually the convolution. This is the best way I could explain it. Probably in your digital signal processing, probably you will know it much better. Okay, so this is our convoluted signal. Okay, now what we'll do, we'll do the other operation, right? Okay, let's go on. For yt, we know. So for yt, we know the received signal, yt. Remember from our previous slide, yt will be xt, which is our transmitted signal, plus some noise is added there, right? Additive white Gaussian noise there. Okay. What is xt here? Xt is, imagine xt, we express it by a0 pt. Remember our previous equation? This is the simplest form. We took xt as a what? Remember xt, expression of xt was a k pt t minus t. That was our complex, complete expression. Now here we are actually taking the simplest from the first bit. If it's the first bit means first pulse actually. So it's a0. So p t, because this t is not yet comes. Okay, this is 0. So pt is our simplest form of our input pulse. Okay, so our yt will be a0 pt plus nt, right? Okay, now if we put it to our rt, then what the rt will look like? So how the rt looks like? We know RT was minus infinity to plus infinity y t minus tau. But here y t minus tau is also this equation. So a0 p. Now you see, so y is just modified here, t minus tau. So y, if I introduce t minus tau here, t minus tau, then what will happen? Pt minus tau will be introduced here, t minus tau will be introduced, right, in this equation. Okay. So p t minus tau plus n t minus tau. This is actually our the first part into h tau d tau. That's our complete equation. Now we have seen in the receiver model that the received signal RT is sampled here, sampled at t. This well-known fact that in digital communication, when we receive the signal, we actually sample the signal at the way the signal was sampled when it was transmitted. So this is our the sample signal, the sample bit. So for our case, it is sampled at t. So if it's sampled at t, then this whole equation changes. So sampled at t. So this signal is sampled at t. If it's sampled at t, then we write r t equal to minus infinity to plus infinity, same equation, A0 P t minus tau plus n t minus tau into h tau d tau. Okay. Okay. Now here ht is multiplied with these two, so I will try to separate it. So minus infinity to plus infinity is 0 pt minus tau h tau d tau plus, I'm actually multiplying this one with put it in with the bracket term, plus n, okay, plus minus infinity to plus infinity n t, is sample at t, so this will be t, so t minus tau h tau d tau. Okay, so we got actually two components here, one component, two component. This is a signal component. You see, our signal is here, signal component, and this is because noise is here, so this is noise component. Now see this impulse response or response of the filter is with both of the term, with signal term as well as with the noise term. Okay, now this is the question. The question is how to choose h tau or design like filter response, or we can say impulse response of the filter or impulse response of the LTI system. How to choose it? Now, while we will be choosing two aim is there. So the aim is aim1. You see, for any better receiver, we are designing a receiver, right? So the signal component should be higher. So the HT, this parameter should be chosen such a way that it maximize the signal power. The whole term should be maximized, whole term, and the noise should be minimized. That's the better filter do. So minimize the noise power. Ultimately, if I increase the signal power and minimize the noise power, what I'm doing? I'm maximizing the signal to noise power ratio. Signal to noise power ratio, SNR. 20 minutes. So I'm increasing the signal to noise power ratio. That's actually ultimate goal, and this is actually the ultimate goal of any receiver. Any receiver we like to design, the main aim is to increase the signal to noise ratio. This is the fundamental like performance matrix. This is actually this one. This criteria is the fundamental performance matrix of a digital system or any system, any communication system. Performance matrix. Okay. Now, so what is the signal here? The signal we just received. So the signal power, signal. What is the signal here? Signal, this one, signal is actually over this part. So minus infinity to this is our signal, is 0 p t minus tau h tau d tau. This is our signal. Okay. So the signal power. So this is the signal. If this is the signal, then the signal power will be. So signal power will be, if I find the expected value and the square. So minus infinity to plus infinity is 0 p minus t h tau d tau. So this signal may contains a complex real or imaginary both part. We want the absolute value. So the square of that absolute value and the expected value of that square will give us the signal power. Okay, if this is the signal power, then we can write expected value of is 0. We are just separating the term, and expected value of minus infinity to plus infinity p t minus tau h tau d tau, and the square. Okay. For imagine we have solved this part before. This part. We have solved this part before. Expected value of a square. Okay. What is the expected value of a square? We term it as a PD. Remember, we solve it in previous equation. So this will be the PD. What is PD? What is PD? PD is the power of the data symbol. PD is the power of the data. Probably lecture 2. There actually we did this. Now you see here P. What is P and what is H? What is P? What is H? Here P is the shape of the pulse, right? The pulse we transmitted, which is a fixed value. And H is the response of the filter. Filter is a physical stuff whose response is also a physical, like fixed stuff. If I give this input, I get like HT. So this is the response of the. So if I give him one input, I got another input. Means this is a fixed. This is a fixed phenomena, fixed value. The design of a filter is a fixed. Means the combination of these two. This is also a fixed combination, kind of constant value. PT is the same pulse, the one we transmitted early. Right? Remember the signal we transmitted, PT, which is also a fixed value, means actually these are the deterministic value. This is not a random value. So these are the deterministic values. Now, what we are trying to do, we're trying to find the expected value of a deterministic stuff, right? So what will happen? So our signal power will be for constant PD. This is equivalent to PD. So this is equivalent to PD. So PD and then this one. So expected value of a deterministic is the deterministic itself. Understand? Expected value of something like average value of a constant is actually constant. So this is the way you can write that value is minus infinity to plus infinity p minus tau h tau d tau square, because this square is there. So now this is actually our complete signal power. So we have derived our complete signal power. So in the next lecture, we will derive the noise power. Once we know about their characteristics, the signal and noise individually, the signal and the noise individually, we actually can better design the impulse response of the filter, or we can better fulfill this criteria SNR. So we will stop here.